Welcome everybody. My name is Ullrich Pfeiffer. I'm with the University of Wuppertal in Germany, and I'm going to present to you, as part of the educational events at the ESSA conference, my talk about SiGe HBT devices, circuits for millimeter wave and THz wireless applications. I will first start out with the motivation, and as part of the motivation I will discuss the properties of THz radiation, some of the device technology options that we have. I will talk about design challenges for circuits, and I give you an application summary before I go into 4 parts of my presentation, which cover not only novel cameras and sources that have been addressed over recent years, but also I will talk about more exploratory work on biomedical sensing, for instance, and also very commercially interesting 6G or THz communication applications that discuss high data rate links and novel polarization diversity MIMO systems. Now what you see here in this slide is the attenuation of electromagnetic radiation over frequency. And you see all the known bands that we have addressed at the lower frequency side in the microwave, millimeter wave range, and you also see the visual part of the electromagnetic spectrum here on the right side. And you can see that here in the sub-millimeter wave band we have, two communities that are meeting each other here, the electronic people, who can probably address, from 100 gigahertz to 1 terahertz circuits very well right now in many of the silicon technologies as well. And of course you have also a lot of photonic people that are kind of moving down from the higher frequencies and trying to implement interesting applications here from their perspective at the much lower frequencies though. Now when you look into the properties of THz radiation, 1 terahertz has a wavelength of 1/3 of a millimeter, which is relatively small, and because of that there's a very low photon energy of only 4 millielectron volt, which makes this radiation of course quite interesting for many biomedical applications. Also what you see is that the peak of the black body radiation spectrum kind of peaks at 1 terahertz if you cool down to 17 Kelvin. And you probably know these Planck radiation laws from your undergrad physics courses. And basically this means that really even very cold objects still have THz radiation inside of them. And a good example here of course is the background radiation spectrum that you see when you observe the background radiation of the universe. Also that, by the way, was measured at a quite a low temperature, but if you translate this into frequency, it still means quite high of a frequencies of 160 gigahertz, because the background radiation is measured for an object that is at the temperature of 2.7 Kelvin. Now, and if you compare all that with X-ray radiation, you see that the energy of the X-ray photons are on the order of 10 kiloelectron volts, which is 7 orders higher than terahertz. And again, so this means that THz radiation is as reasonable, harmless in this sense. And another interesting thing that has been observed here as part of the Event Horizon experiment, which was the radiation that was emitted from a black hole, and that was also done at 240 gigahertz of the Messier 87 galaxy in 2017. You may have seen this picture here, and it's quite interesting to keep in mind that this is a very interesting frequency range where we are discussing 6G communication, for instance, right now. Now, in summary, basically, when you think about all these radiation properties, you come to the conclusion that basically every object around us emits THz radiation, and we should not be afraid about THz radiation in this sense, because really it is around all of us. And the power that is emitted though is quite low, but it's non-ionizing and therefore not harmful. Now, what is the problem in general when we move to the higher frequency range, and in particular from an electronic engineer point of view? And you know that electronic systems traditionally really would benefit from higher frequencies, and this is because at higher frequencies you have a higher channel capacity. You also have a lower latency. You can implement new sensing phenomena. You have a better spatial and temporal resolution in many applications. and we also have an increased dynamic range. But to really get the benefits at these frequencies, we need to have faster transistor speeds. We need to have better IC processors, better packaging and system design tools. And if you don't do that, if you don't get that improvement, and you are trying to still push to higher frequencies, you have to face significant challenges. And that is caused because you have a higher power consumption typically and thermal density problems. Also, you have to compromise on the system complexity. So most of these systems that you see today or you have seen in the past are most likely quite simple and are built from rather bulky and costly millimeter and sub-millimeter wave components. So we want to basically change this silicon community, and therefore we are looking into electronic device technologies, which are shown here on this slide. For instance, you have, of course, the working horse here over many years, which is related to the 3-5 semiconductor materials. There are different device modules you have available. There are indium phosphide HEMT devices, for instance, which are kind of leading the record on the Fmax of the technology of 1.5 terahertz. We have seen even a few years back in 2015 that you can implement amplifiers at 1 terahertz with 9 dB gain. And these amplifiers can generate something like 0.8 milliwatts at a terahertz. There's also gallium nitride, which have also high power delivery features with an Fmax of 0.6 terahertz. Double HBT transistors is 1.2 terahertz. And that, of course, is very well performing when you compare that to silicon substrates. Silicon substrates, you are rather on the lower side of the Fmax with CMOS, bulk, SOI, and FinFET devices. They are typically below 350 gigahertz. And, substantially better, though, is the performance of the SiGe HBT device, which also can be integrated together with CMOS. And they have shown a cutoff frequency of 700 gigahertz. And here you can get something like 10 milliwatts at 240 gigahertz and 3 milliwatts at 320 gigahertz. Of course, there are other technologies available like heterogeneous integration of indium phosphide. So you combine the indium phosphide with the silicon side. Or you can do electronic photonic integration, which kind of brings together these photonic and electronic worlds. You can implement modulators, waveguide, germanium photodiodes, and all combined with the silicon back end of transistors for signal processing and data readout. Now let's look into the silicon germanium technology evolution. And I would like to start out at a time when I was still working for IBM in 2000. We had at this point transistors available for circuits with an Fmax of 200 gigahertz, and after that I kind of moved back to Europe, and there were a number of European projects that were trying to improve the performance of those devices further. And in 2010 roughly we had something like 500 gigahertz available. And the latest results were achieved by a follow-on project which was called .7, and with these devices we were actually reaching up to 700 gigahertz of max. And you see that with all these new generations that were developed, new applications kind of emerged. Initial applications were a lot focused on 60 gigahertz communication and 77 gigahertz automotive radar, and now that has been substantially moved up even into the terahertz range. And now we are really talking about 6G and terahertz communication at around 300 gigahertz, which of course is something that we will now, from 2020 on, now really look globally into this. Whereas the initial results here were rather isolated, but now there's a global economy that kind of pushes into this higher frequency and terahertz domain. Now, how do these faster transistors really help us when we think about designing circuits? And of course, there are maybe two groups of circuits you can think of. Some of them are just fundamentally designed circuits, and there are other groups of circuits that are subharmonically driven. So you're operating in subharmonic circuits on a higher harmonic number. And of course, when you have better performing circuits available, you can have, let's say, higher carrier frequencies for the fundamental circuits. You can also get more gain per stage, which translates into fewer gain stages. And that helps, of course, the bandwidth. You can also use the performance to lower the DC power consumption. That also gives you higher efficiency. you can also get larger output power because you can make your devices larger, and you can deal with the parasitic effects much better, and also you can have lower noise figures. For the subharmonic circuits, you operate basically at a lower harmonic number, which kind of also turns into a power generation benefit, and you can also have lower noise figures in subharmonic receivers. So definitely this helps a lot if we have better performing devices. Now, when you look into the applications scenarios that we have addressed, and I've been working now in this field for many years, and we started out basically looking into imaging applications first, millimeter wave and terahertz imaging sensing applications. The key applications here are non-destructive testing, kind of through imaging of objects, which can also be thought of in the security domain. Biomedical is something we will talk about. There was a lot of imaging in space already. Material characterization, spectroscopy, and super resolution imaging are key application areas. And when you extend this sensing into the third dimension, you can think about radar applications, and there also we see that we move into the higher frequencies for automotive, remote control, gesture recognition, 3D imaging, patient monitoring are things where we need better range resolution and spatial resolutions, and therefore these higher frequencies are a lot better than lower frequencies. And of course, the communication is something there where we have this recent interest, also because we now have a new IEEE standard, 802.15.3d from 2017, where we specifically mention the 252 to 322 gigahertz frequency band. And that is used for links up to 100 gigabits per second, and combining these links in networks will bring us up to terabit per second wireless communication, and this is something where these higher frequency bands are a key enabler. Now let's first look into some of the history of the devices that we have developed at my university in Wuppertal. So we have worked really a lot on integrated THz detectors. We started out in 2008 with our first focal plane array that we designed. At that time at a quarter micron bulk CMOS technology with a NEP, which is the noise equivalent power of the detector of about 400 picowatt per square root of hertz. Now, since then, we basically had improved this over recent years, not only on the sensitivity, where you can see that we had record numbers now, even by using the bipolar SiGe HBT transistors down to 2 picowatt per square root of hertz. They basically have enough sensitivity to do even passive imaging. But we also worked on system integration, and one of the examples were just published at the ISSCC in February earlier this year, where we developed a light field camera, and I will discuss some of that and what kind of benefits these systems finally have. Similarly, on the source sizes, also we started out early in 2010 developing power generators, basically, that were trying to kind of use a reference frequency, multiply it up, and try to get as high as possible here. We also used oscillators, free-running oscillators, triple push oscillators, and we moved into arrays. And also here we looked into really more complex systems for imaging applications, and there also we published a 240 gigahertz source array last year at the ISSCC, and we're also going to talk about the 64 pixel terahertz source array for 2D imaging as well. Now, as you can see, the key benefit here is the programmability and building smart arrays, and to use systems on a chip. Now, before we go into some of the benefits maybe of incoherent operating circuits, I would like to maybe give you a little bit of a history of terahertz imaging, how that was basically performed over these, let's say, roughly 10 years. So when you look back, the early work that we have published was mostly working with a single transmitter and a single detector. So the only way to do imaging with that, you would have to scan basically your object through this focal point that was generated in the object plane. And then after that, we decided to use a single source, but use multiple detectors on the receiver side, which gives us basically a camera or a focal plane array. The benefit here is, of course, you are much faster because you can operate in parallel, but you have poor SNR because all the power from the transmitters needs to go through the same object basically in parallel, and therefore the power illumination at a certain object point is much lower than in this first case. Now, there are other ideas, of course, and that is basically the combination of an array on both sides. Not only the camera, you can also use THz arrays on the left side, and these arrays can be programmed as well. And of course, here you have much better SNR, and you can still perform images at a high video rate. Now let's look into the specifics of these cameras first, and we'll cover CMOS and silicon germanium cameras. So here's an example of an even commercially available camera that we have created out of a startup company at my university. There are some images that you see here that were recorded in 2017 at the IMS conference. You see that here we used 1 terahertz source to illuminate this CMOS camera, which was made out of 65 nanometer bulk CMOS. And here you can see the real-time image that was recorded here on a regular Windows PC with a USB device. So basically, THz technology can work with CMOS. This is not a surprise. We have shown this for many years, even in very standard commercially available process technologies. Yeah. Now, what about these coherent receivers, and what are their benefits compared to incoherent receivers? So here are a few examples how they are implemented. So here on top you see a Global Foundries 22 nanometer FD-SOI antenna coupled direct detector compared to a SiGe HBT direct detector. The lower one actually has a or has two polarizations included, so you can do cross-polarized imaging with this as well. And when you compare their sensitivity with heterodyne receivers or coherent receivers, that you see that the NEP here of detectors is still much worse, of course, than those of coherent receivers. Yeah? Where basically right now most of these detectors are above 1 picowatt per square root of hertz, they still perform much worse than the heterodyne counterparts, which is about a difference of 50 dB here. Now, so incoherent receivers are about 50 dB worse in NEP, but much smaller and basically zero power. So you basically can just implement them on the footprint of an antenna, whereas coherent receivers always need to have a mixer and a local oscillator that kind of creates a coherent reference signal, and that makes them much more bulky, and that's why these incoherent receivers are much more preferred for large arrays. And that is an example here where we have actually built a 1024 pixel camera SoC that was published here in February at the ISSSC conference. This implementation basically includes all the reader electronics for these cameras, and it kind of is a very tight footprint. So you can see this is all integrated together on a silicon lens, and it's very tiny. You can hold it, basically between your fingertips. So it's not really bulky if you compare this to previous THz circuits. Now, the main benefit in this design is that you can not only work with an individual camera, you can also combine these cameras in a super array. So here you see an array of 3 by 3 of these cameras, which gives you in total 9,216 receiver channels. And you can see here that you receive all these images from these cameras in parallel. And of course, that gives you a lot of capabilities to do numerical computation and image processing on the data that you're collecting here. Also, when you think about wireless communication, 9,000 channel is really something that's very massive. And that, of course, is also a good argument why terahertz massive MIMO communication system can be integrated with a lot of channels, basically. Now, this work is also funded by a European ERC Advanced grant, and of course, there will be a lot of more results coming up in the coming years now in this area. Now let's look into the source side. Also here, CMOS and SiGe sources are being shown. I would first here on the top show you some work in 65 nanometer CMOS. This is also commercially available, and below here there's an IHP 130 nanometer SiGe device. In both cases we use harmonic oscillators to create higher harmonic frequencies, and again here you can also see how that has been developing over the frequency. You see that you basically have a roll-off here of 20 dB per decade, but when you look at all the record results that we've seen, all of them are basically from arrays, and of course arrays can be either locked or they can be unlocked, and again here you have different kind of benefits, of course, when you start operating things in a coherent or uncoherent way, and that is something that can be used also to the benefits in terms of trying to use an incoherent illumination, where you basically avoid some of the specular reflections that you typically experience in imaging systems. And one of these examples of a programmable source is shown here. So here we have 64 pixel THz source, which we've published here last year at the ISSCC. You see the implementation of the oscillator coupled pixels to an antenna. They are all linear polarized, and you see that this is all integrated here on FR4 boards. It's quite small, but there are, of course, some issues, and some of them are related to the thermal emission of these chips, and that is shown here. So when you start increasing the number of pixels by turning one on at a time, and you use that kind of to kind of increase the overall output power, then you see that you will hit at some point into some thermal compression. So in this design we have reached something like 10 dBm, which gives us a temperature at the surface of the lens of 70 degrees, which is quite hot. Overall the DC power consumption is 4.5 watts for that source, but they are all operating at 420 gigahertz. So that is a very high output power, and if you start cooling them you can even reach up to 15 dBm. So that's another plus 5 dB for the total output power. And with that, of course, you can start thinking about diffused illumination scenarios for imaging systems. So please refer back to the initial slides I've shown you about how to create images here, terahertz. You see that here we have a source array that kind of provides a diffused illumination for the object plane, and then we have a focal plane array on the other side. And you can basically, depending on how you configure your source, you can change different kind of illuminations from a more flat pattern versus some pixeled illumination patterns as is shown here in this figure. Now with that you can of course build basically terahertz see-through imaging system fully in silicon. You can also apply computed tomography imaging algorithms to even get 3D information out of it, and you can use the numerical data on the receiver side to look into compressive imaging algorithms, and that is a huge playground that you can address these technologies. Now let's move into another application area, which is biomedical sensing now. Now when you think about the imaging results that I've shown you before, they were all, of course, in the far field. And in the far field, you see that because of the wavelength, you are limited to resolutions in the order of about 1 millimeter. So this is all here shown on the right side. And if you want to look at something that is related to biomedical effects, to the cell of the human tissue, for instance, or to proteins, virus, or DNAs, you have to go much lower in the resolution, and that is a problem for the far field because you cannot bridge the diffraction limit here. But if you go into the near field, of course, you can actually try to overcome this limit, and I would like to show you how we have done that. The first idea was to use here a splittering resonator. This is basically like an LC resonant tank, where you bring the gap very close to your desired object under test. And then when you bring some material close to this gap, you are basically detuning the resonance frequency of this resonator. So that's a very well-known kind of effect in engineering. And we have brought this to the test by integrating lots of these splittering resonators in a silicon IC. Here we have basically integrated them in a linear array. We have actually had two of these arrays, kind of mirrored, so that we have a tighter pixel pitch here of about 50 microns on the y-axis and 110 micrometers between these two line arrays. Then we have all assembled that. We have glob-topped the wire bonds, and then we were able to actually bring something in close proximity to this sensing array. And the question really was, is this possible in the first place, and can we use this to acquire some information about the dielectric properties of materials? And of course, what you do is to mount this on an AFM type of microscope, and then you can do raster scanning basically. And this is one of the first images that we recorded, primarily to find out what is the resolution that we are finally achieving on this. And we have been testing this, and we got something like on the order of 15 micrometer when you take the 10 to 90% rise and falling edge criteria here on some step function of an object. Now, to finally show how this works in real time, because this is an SoC, it can really be operating in real time. We have mounted this on a small board, and you can even now put your finger on it. And here you see the 128 kind of sensor pixels. And when you start moving your finger to the left and to the right, you see that the grooves and the riddles of your finger kind of create this sensor response here along the line. And of course, when you start taking this data precisely, you can actually acquire a THz near-field image of your fingertip, of your fingerprint, and you can compare that to an ink print, and you of course see that you can get the same information. Now, this is of course not yet some sensor that measures some material properties, but it just gives you the image with a very high resolution that we have not seen before in any silicon application. So far, everything was done in the far field with a resolution of only in the range of millimeters, sorry. And here we have the resolution in the order of tens of micrometers, so much better. Also, you can apply, of course, a cleaning with alcohol here. So when you move across this surface, you see how these sensors kind of respond. And ultimately, of course, we want to do biomedical sensing with this, and one of the applications that we have in mind here is delineation of cancer margins in breast cancer surgeries. And here we work together with histopathologists who are actually taking typically stained images of cancerous tissue, and they observe that under the microscope. And with our sensor, of course, you can create THz images. And we are now working together with these pathologists to compare the THz image with the microscopic image to see if there are some specific features that are typically and characteristic for the THz range that help us to differentiate between cancerous and marginal tissues. Now let's move on to the last part of this presentation. And of course, when we think about wireless applications, we mostly think about communication. And I already motivated that we, of course, were working a lot on this topic for many years. While I was working at IBM, we started out looking into 60 GHz application in 2006. And when you see how that has been improved by some of the publications that we have published here, see that we have now reached in 2020 at data rates that are much improved from what we had in 2006. We went from 4 gigabits per second basically to 110 gigabits per second. And I would like to show you some of these circuits and show you some of the link results. So overall great performance, but yet they are not, of course, commercially available. So there's still a lot of things to work on and to improve in the future. The initial idea that we had, of course, was to rather build simple circuits. So we were looking into typical Gilbert cell mixers, double balanced Gilbert cells in a quadrature configuration to use complex modulation with I and Q signals. Though if you don't have a lot of linearity at these high frequencies, you have to stick to rather low modulation orders. So in turn that translates basically in a lot of bandwidth, but because at these higher frequencies we have a lot of bandwidth, we thought this should be a first step to try. Don't focus too much on linearity, try to look into rather large bandwidth. And there are some issues, of course, for these receivers if you're trying to address tens of gigahertz of RF bandwidth. Now the first issue you can immediately see when you try to calculate the link budget for QPSK modulation, so rather simple modulation. And if you go through the path loss formula here, you take some of the numbers into consideration that you typically can achieve, some TX power between 0 dBm and 6 dBm, let's say, and rather high noise figure though, because our devices have very low gain as we modulated at the beginning. And if you have only one channel, see there you have to cover rather large RF bandwidth, and that of course translates in the high noise floor on the receiver side. And the only way really to get you to a large distance, not only in the range of only millimeters, but rather meters, you would have to increase the antenna gain substantially. So 0 dBi, isotropic antennas are not sufficient to give you some distance. So you have to move into high antenna gains, and lenses are a good alternative here as well, which we have known from the imaging side. So you can get something fairly easily in the order of 25 dBi on the transmitter and also on the receiver side. And when you do this, you are getting into the range here of a few meters. Nevertheless, there are a lot of circuit design challenges remaining. There's a lot of trade-offs, of course, that matter in terms of output power, noise figure, bandwidth. And of course that affects the range. And also now you can combine that with all the challenging aspects and the trade-offs that you have from the packaging side and the antenna design side. Now let's first look into some of the earlier work that we've published in 2015 and 2016. Now we had IQ transmitters combined with primary on-chip antenna feeds and then a secondary silicon lens that was attached to the back side of the silicon die. And then we had various kind of receiver implementations. At first we thought about implementing low noise amplifiers. There are a few challenges, of course. First of all, you need to align the receiver amplifier with the transmitter amplifier very well, and that is a bit challenging if you really have different kind of design techniques for amplifiers, like power amplifiers and noise match in the receiver. And then finally we decided to completely remove the receiver and go into a mixer first receiver architecture as shown here on the lower right side. And then we did a lot of comparison between the pros and cons between these architectures. And here you see some of the packaging examples that are applied. Again, this looks very similar to an imaging system where we also use lenses, but here we use the silicon lens to give us this high antenna directivity that we need to bridge over in a large distance. Here I would like to show you some of our first imaging results that were actually, communication results, sorry, that were done in 2016. So here we just used a EDT kind of antenna signal that was sent into our broadband IF and was directly transmitted then or mixed up to 240 gigahertz and then transmitted here from the transmitter to the receiver side. And the nice benefit, of course, is it goes to cardboards very easily, but of course it's being blocked by water. THz is absorbed highly by water. So when you put in your hand, of course, you're blocking the signal and the link will be lost. Just to show you, the carrier frequency here is at 240 gigahertz. Already in 2016, we were doing these kind of experiments. But at that time, though, it was not easy to measure the achievable data rate for us because the baseband is quite complex to implement. You need very fast ADCs to cover this large RF and then also IF bandwidth respectively. So this is something that we have addressed in the coming years, and we've now finally also published the data rates that were feasible with this hardware. And here you see some of the summary of the measured data rates that we were able to achieve here for different kind of modulation orders. And the record results with this hardware was up to 100 gigabits per second here, although the EVM was still quite high, 17%. Ranges were at the meter level, 1 meter and 1.8 meters here for 80 gigabits per second. Now I would maybe just quickly discuss some of the issues for the circuits. First of all, you have to face various kind of problems when you think about creating the reference local oscillator signal. Of course, you can try to implement oscillators that may be spectrally quite pure, but they are not necessarily very widely tunable. So we were designing a lot of multiplier chains for the reference signal generation, and they typically suffer from spurs at various kind of integer offsets here from the desired harmonic, which is here in this case at time 16 LO. And all these spurs kind of create kind of unwanted modulated signals that are kind of overlaying to your desired signal and the transmitter output. And they also kind of are mixed down then to create some interference level. And of course, in the end, what really matters is not only the SNR, it is really the signal to interference level. And these harmonics, of course, have to be really suppressed in order to give you good signal to interference on the receiver side. Also, you need to worry about where is your external reference signal to not move the external reference into the IF bandwidth. And there we have done some of the link tests. You see some of the data rate that we are getting here for 16 QAM, and here you see some of the record results here of 100 gigabits per second. Now with this hardware, when you look about the desired channels that were part of the 802.15.3d IEEE standard now, that covers frequencies from 252 to 321 gigahertz, you see that we are now covering with this hardware 4 channels, where each channel has a bandwidth of 2.16 gigahertz. If you combine these channels, of course, we would be able to cover up to 8.6 gigahertz of RF bandwidth. And of course, you see there's a lot of gray stuff still, so there's a lot of rooms for everybody to look into to increase the carrier frequencies up to 300 gigahertz basically to cover the remaining bands. But the RF bandwidth certainly of these chips are high enough, so it's merely a matter of moving up the carrier frequencies in order to address all the channels that are allocated right now as part of the standard. Another work that we were looking into is polarization diversity MIMO. And of course, the question here that we were looking into is how can we improve the spectral efficiency? I try to motivate to you that when you don't have very linear circuits, you would have to run with a rather low modulation order. And to increase the linearity is not necessarily an option with these devices. So another way would be to just basically parallelize the system and have a number of parallel links, which although they need to be orthogonal to each other in order to use the same air channel or the wireless channel to increase the data throughput through the air. And one way to do this is polarization diversity MIMO, where you use left and right hand circular polarization at the same time. And this is shown here in this block diagram. So you have here in green a transmitter and in red another transmitter, and the same thing on the receiver side. You have 2 receivers and you go through a circular polarized antenna here on chip. Now the circuits here that we use, just to show you some of the schematics here, are still pretty standard. These are just Gilbert cell up conversion mixers. So we don't really do something fancy here. We just want to evaluate the circular polarization. Also on the receiver side, we were using here mixer first architecture. So we are going in directly here with the RF signal into the switching cords, and we use here also double balanced Gilbert cells to move down to the I and Q channels. So also here it's rather simple circuits, although the design at these high frequencies makes it challenging again, because you have to consider all the EM effects of the implementation of the back end of the line and so on. And the modeling accuracy of the device is not necessarily as good as we would like to. In this slide, you see some of the chip micrographs of the implemented circuits. On the top, you see the receiver chip. On the bottom, you see the transmitter chip. And of course, here in this configuration, you need to worry a lot about crosstalk between the green and the red channel. And that is challenging because of the dual polarized antenna that is required for the circular polarized radiation. So if the actual ratio here is not perfect, you will get crosstalk from one channel into the other. So depending on what the actual ratio is of the antenna system, you get crosstalk, and that crosstalk finally translates into an EVM that kind of limits the data rate again. So therefore, the antenna implementation together with the packaging is a very crucial part of the design of the chips. And here again, you see how these are packaged, similar to the linearly polarized chips that I've shown you before. We glue the chip to the lens, and the lens is glued onto an FR4 board. And then you see the radiation kind of comes out through the backside of the die into the ceiling lens and then out. Now the first thing you can do is you can do an RF characterization, which is shown here. So on the left you see output power versus frequency for different kind of carriers. And you see that there's a bit of an asymmetry here on the transmit power. And this is understandable that you can create more power at lower frequencies, but you have a little bit of a problem creating or keeping the output power at the higher side of the carrier. And when you look to the receiver side here, you also see the conversion gain and the IQ imbalance here over frequency. And again, this data is also shown for various kind of carrier frequencies. Now, then next I would like to show you some of the implementation of the antenna design. And here you see some of the HFSS simulations that we typically do to simulate the performance of the antenna. You can actually see how the circular currents kind of are generated inside of the dielectric stack of the back end of the line. And we do this here also by including all the feed structures and hybrid design to make sure that that is all co-designed together to give us a really perfect radiation pattern and low crosstalk between the different circular radiations here. Now, finally, of course, we also want to have a very circular radiation pattern to give us good directivity. Here you see the two cuts that were taken and also in 3D plotted here. You can see that we get high directivity here on the order of 25 dBi. Now finally, we do the data rate tests in a 6G communication test bed that we have set up at my university. You see here hardware from Tektronix that is being used to feed the I and Q channels from the transmitter and the receiver. And in this one is also available for people that are interested in collaborating with us. Please check out this link here for further information, and you can already start getting in touch with us in case you would like to use some of the equipment and also maybe try out some of your own modulation with this hardware that we have here developed. Now finally, I would like to show you the data rate results that we were taking in this testbed for this circular polarized MIMO system. Here you see the left-hand circular polarized channel, and on the right chart you see the right-hand circular polarized channel. You see the EVM measured for various kind of carriers and data rates, or basically symbol rates. And you see that the record result here was 55 gigabits per second in each of the channels, and when you start adding these channels up, you get up to the 110 gigabits per second, which is the record that we have achieved so far. Although theoretically, I have to say, you should be able to get something like 100 gigabits per second in each of the channels, which should add up to 200 gigabits per second. And one reason why we didn't get that is because there are only single-ended signals being used, which is more like a technical reason and not that much of an RF performance limitation. Here you see just some cancellation diagrams here for left-hand and right-hand polarization. And also you see here the 55 gigabits per second, kind of that prove the quality of the link. Now finally, if you show the results here that we're able to achieve, and I show you just here an example for the 100 gigabits per second single channel, and you see that with an dBi of 26, you can get up to 1 meter. And of course, if you want to go further, you would have to increase the directivity, let's say, to 50 dBi, which would then overcome the path loss, and you would be able to reach up to 100 meter. But of course, for that, you would have to increase the size of the lens, and you can use a Teflon lens or a metallic mirror in the end to get up to 6.5 centimeters, for instance. So here also is a final summary of our work, and you see the record results here was at 110 gigabits per second. And that finally brings me to the conclusion and summary of my work. You have seen in the presentation that there is a lot of improvements over the last 10 years, basically on the sensitivity of terahertz cameras and CMOS and silicon germanium. Also, sources have improved by 2 orders of magnitude in output power and also carrier frequencies over the last 10 years. We are now at the level where we can implement fully integrated THz systems on a chip, not only for imaging, but also for sensing. And there are plenty of novel THz applications that we can think of. Some of them, of course, are also related to commercially very interesting applications. In particular, THz communication as part of the 6G standard is quite interesting, and you've seen that you can achieve up to 110 gigabits per second over a few meters in silicon germanium. 100 meter is possible, but you need to improve the antenna gain. Now, there are a lot of still future challenges remaining. In particular, we need to improve link impairments, for instance, to give us much better reliable links in the future and to further increase the data rate. Now, I just want to give you the reference list here in case you want to look up some of our results and papers. And with that, I would like to thank you for your attention, and also I would like to thank all the people that contributed to this work at my university, in particular the PhD students and the funding agencies that are providing us with the resources that we need for this work. So thank you very much, and I look forward to the discussion. Thank you.